Okay, we're going to look at two different examples of solving differential equations that have complex roots and how we design parameters or to figure out parameters that are going to meet design constraints. So the first example, we have a circuit and we want to figure out what is the capacitance and what is the inductance. So we need the capacitance and the inductance. And our goal is we want the circuit to have oscillations of 500 cycles a second, and we want the oscillations to decay like e to the minus t over 100. So the question is what values of C and L will achieve this objective? In this particular case, we're given the circuit diagram, and we're assuming that the voltage is zero. So the idea is you charge up the capacitor and then basically let it go and then see what happens. Later on, we're going to see what happens when the voltage can change in time. But for now, the first step is you just assume a direction, and basically this is just following what we did before. And if we get it wrong and we get negative numbers, that just means we need to reverse the order. So just choose a direction and just stay consistent with that. So as we go from here to here, the voltage drop is zero because the voltage in the battery is zero. As I go from here to here, we're assuming there's some charge in the capacitor, and that voltage drop is going to be Q over C. Now as we go from here to here, there's going to be a voltage drop given by the current times R, so that's Ohm's law, but the current is just the derivative of the charge, and then the resistance is 10. And then finally, as I go across the inductor, the voltage drop is going to be L times the rate of change of the current, which is the second derivative of the charge. And that total voltage drop, is, as I come back to where I started from, has to be zero. So that's Kirchhoff's loop rule that we're applying here. So rewriting that, if I multiply through by -1, let's put this in the form that we're used to seeing. So this LQ double prime plus 10Q prime plus Q over C is 0. L, 10, and C are all constants. So this is now a second order constant coefficient linear homogeneous equation. So I can just assume that I got a solution in this form. And here, because I don't know what L and C are, I want to figure out values of L and C so that the real part will give me decay, and I know in advance I'm going to have an imaginary part because I have oscillations. So I'm basically just going to plug this in, look at the roots, and the roots are going to have L's and C's in them, and I'm going to separate the real and imaginary parts to give me the behavior I'm after. So let's see. So Q prime is going to be RE to the NT times N. Q double prime is going to be RE to the NT N squared. Plugging this into my differential equation, I'm going to have L times Q double prime, so RE to the NT N squared, plus 10Q prime, so I have RE NT times N, and then plus Q, RE to the NT divided by C is 0. RE to the NT, RE to the NT, RE to the NT, all that's in each and every one of these terms, so I can factor that out, leaving me with Ln squared plus 10n plus 1 over C. I don't want that to be 0 because that would be my charge. I know that's not 0, which leaves this quadratic equation, and L and C are constants. I'm just going to use the quadratic equation to get the roots. So B is 10, so I have minus 10 plus or minus the square root, B squared, which is 10 squared, minus 4 times L times 1 over C, all over 2L. So these are my roots. because of this, I know the real part has to be minus 1 over 100. Because it's going to oscillate at 500 cycles per second, so let's see. That means the period has to be 1 over 500, because the way to get 500 cycles each second is going to be, so 500 times the period equals 1 second, which means that the period is 1 over 500. So that means that the imaginary part times the period equals 2 pi. So I am going to have two equations for that and this, and I'm going to use these two equations to figure out my two unknowns, L and C. So let's rewrite this. It's a bit of a mess now. I have N is minus 10 over 2L plus or minus 1 over 2L times the square root of 10 squared minus 4L over C. I know I have oscillations, so that means I know that this has to be negative, which means then I can factor out a negative 1. And I can pull that out as my I. So minus 10 over 2 is minus 5 over L plus minus 1 over 2L. I pull out this negative 1. It's going to give me an I. I'm going to have 4L over C, then the 10 squared is 100. And I know it's going to decay like e to the minus t over 100 and oscillate with a period of 1 over 500 per second, or seconds. Okay, so the real part means that my oscillations are going to, the amplitude of the oscillations are going to change like that. So it's the exponential of the real part. And for the complex part, I know that when I take the period times this, the period is 1 over 500, that has to be 2 pi. Right? This is basically the T omega I know is 2 pi. So since this is got to be equal to minus e to the minus t over 100, I get my two equations. The first equation is that minus 5 over LT is equal to minus t over 100. And this gives me my second equation, which is 1 over 1,000 L. This comes from the 2L times the 500 times the square root of 4L over C minus 100 is 2 pi. So I'm going to use this to figure out L. I'm going to plug that into here and use that to figure out C. So we can divide through by the t and the minus 1. I get 5 over L is 1 over 100. Multiply both sides by L and both sides by 100. So L is 500. Okay. So, sorry. And now, focusing on this part right here, I'm just going to plug in L equals 500. Be careful, keep track of that. So L is 500. Square root of 4 times L over C minus 100 equals 2 pi. And now my unknown is C, and I've got to solve this for C. So let me multiply both sides by 1,000 times 500. So I get 2 pi times 1,000 times 500. I'm going to square both sides to get rid of the square root. So 4 times 500 over C minus 100. It's going to give me 2 pi squared times 1,000 squared times 500 squared. Let me add 100 to both sides. So I can write 4 times 500 is 2,000. So I get 100 plus 2 pi squared times 1,000 squared times 500 squared. And I'm going to multiply both sides by c. This whole mess is 100. Stays the same. That's 500 squared. And divide through by all of this. So I get c is going to be 2,000. All divided by 100 plus 2 pi squared times 1,000 squared times 500 squared. Okay. So I now have L is 500 henries, and my capacitance is this many farads. Okay. Second example. I've got a spring mass system, and in the spring mass system, I know that the spring constant is 0.2 newtons per meters, and I have a goal that I want this thing to oscillate twice every 3 seconds, and I want the amplitude to decay like e to the minus t over 2. So first thing is I'm going to draw a picture. I've got some mass of mass m, spring constant k, and I've got some friction force gives me by the velocity, and it's proportional to the velocity, so I've got the b. Newton's second law, mass times acceleration. So the acceleration is going to be x double prime. What is x? Oops, so I'm going to assume at equilibrium at 0, x of t is my displacement. So because it's now displacement, the force, let me do the free body diagram. So I've got a force due to the spring and a force due to the velocity, which is air friction, and I'm assuming that's going to be proportional to the velocity, and it's going to be in the direction opposite of velocity, so it's going to be minus b. So ma is equal to the net force. It's going to be minus kx minus b times x prime. In this case, I know that k is 0.2. So this is minus 0.2x minus bx prime. And now let me put this in a form where I can work with it as a differential equation. So I'm going to add 0.2x and bx prime to both sides. It's constant coefficients. It's linear and it's homogeneous. So I can assume an exponential function. And the question then becomes what values of m and b will allow this thing to decay. So when I find the roots, the real part of the roots have to be minus 1/2 to satisfy this. And the imaginary part is going to have to give me the period so that it oscillates twice every 3 seconds. So I know the real part of the roots are going to be minus 1/2. And for the period, so I'm going to have 2 oscillations, so 2 periods is going to add up to 3 seconds. So the period is 3/2 a second. So coming back to here, I have x prime is re to the nt times n. X double prime is re to the nt times n squared. Plugging into my differential equation, I'm going to have m re to the nt times n squared is m times the acceleration, plus b times the velocity is re to the nt times n, plus 0.2 times the position is re to the nt. And by Newton's second law, that has to add up to 0. Every term has an re to the nt, so I can factor that out. So I'm left with mn squared in the acceleration term. Friction term is b times n. And the spring force just gives me 0.2. That is my position. Right, so I don't want that to be just 0. So that means this thing has to be 0. Now, using the quadratic equation, I'm going to have minus b plus or minus b squared minus 4 times that all over 2 times m. And again, I have oscillations, so I know that the thing in the square root has to be negative. If that's not the case, then there won't be oscillations. So let me break this up. Okay, so this is negative, so I'm going to factor a negative 1 out. That way I will know that this is going to be the real, and this whole thing is going to be imaginary. So let me do that. So what do I have? I have n is minus b over 2m plus minus 1 over 2m square root of b squared. Now I have 4 times 0.2 is going to be 0.8 m. I know that's negative. Right, if it's not negative, I won't have oscillations. So let me factor out a negative 1. So now this is equal to that after I factor out the minus 1. And this 0.8m minus b squared is going to have to be positive if I want to get oscillations. So the square root of minus 1 gives me an I. I get a 0.8m minus b squared. So this is the real part. That's the imaginary part. I know that e to the minus b over 2mt has to give me my decay. In the original question, this says that it has to be e to the minus t over 2. This term here is my imaginary part. So I'm going to have cosine or sine of this. So when I multiply that by the period, which we decided was 3/2, that has to be 2 pi. So now I have 2 equations, 2 unknowns. I'm going to basically solve this in terms of b or m and plug into here and then solve for the 1, which gives me the other. All right, so basically this is only going to be true if the exponents are the same. I'm going to assume t is positive. So multiply both sides by negative 2m, and I get the b has to be equal to m. I can now plug that into here. So everywhere I see a b, I'm going to replace it with m. So the b squared becomes m. And this expression now looks like this, and I'm going to just solve this for m. So let's see, I'm going to multiply both sides by 4m divided by 3. So I have 2 pi times 4m divided by 3. And let's see, that becomes 8 pi over 3 times m. To get rid of the square root, I'm going to square both sides. So I get 8 pi over 3 squared times m squared. Now note, I'm going to assume the mass is not 0. If I've got a mass of 0, that's a problem. So I can divide out an m. Now I can add 1 to m to both sides. I can factor that m out and divide both sides by that. So I get m is the 0.8 divided by that whole mess. And I know that b from here is going to be the same thing. So this is what kilograms, and b is just the coefficient for the the friction term, so it's going to be exactly the same thing. So let's see, when I multiply that by the velocity, I have to get newtons.